This is lecture 10 on data conversion, first part, part 1, at the University of Texas at Austin for the class on real-time digital signal processing for the spring 2014 semester. So this is kind of midway through the lectures for this class, and we've already covered filtering, we've covered quantization, and now we're going to combine those two into data conversion. Data conversion includes converting from analog continuous time signals to digital discrete time signals. It also includes the dual of that, which is to go from digital discrete time signals back to analog continuous time signals. Good examples of this would be singing in the microphone or speaking in the microphone, as I am now. And the microphone is picking up the pressure waves by means of a transducer. That transducer converts the pressure waves into electrical signals, basically current and voltage. We sample and quantize that, so we take the current and voltage from the transducer, which is in continuous time and analog, and we go ahead and pass it through an analog to digital converter to sample and quantize that information. Now we have a digital discrete time stream that we can process, compress, and otherwise embed in this video as you're watching. So the opposite would be, as you're listening to this, we now have a discrete time digital signal, and you'd like to play that back over headphones or possibly speakers. We want to convert that discrete time digital waveform for the audio back through a digital to analog converter, and then back through a piezoelectric or some other device that will take the current and voltage from the digital analog converter and get it back into pressure waves so that we can hear it. So again, either through speakers or through headphones. So this is data conversion, and I've pulled a few, in part 2 mainly, which is the next lecture, I pull a lot of information from Ken Pullman's book on principles of digital audio. And there is a newer edition than the one that I referenced, but the figures come from this older edition. So again, this is from Ken Pullman's book, and really useful book if you're interested in this topic as it applies to audio. It turns out some of the lessons learned in audio also apply very well in image processing, and that's going to be part 1 today, to give a visual insight and visualization of data conversion using images and image processing. And then the slides were done in conjunction with, I'm Professor Evans, and this is in conjunction with one of my former PhD students, Ming Ding, now Dr. Ming Ding. Okay, so let's talk about right away, the concept here in imaging is to convert a high resolution image to a lower resolution image for display on a monitor or a micromirror device if it's handheld, or to print the high resolution. And when we print, we're really left with the background of the paper, and then we either put ink on a particular part of the page or not. So for black and white printing or grayscale printing, we'll put black ink on the page if it's a white background or not. And so it's a binary decision as to whether we put a dot on that particular part of the page or not. This is known as halftoning. We can extend this to color by printing cyan, magenta, and yellow, and possibly black ink, or go to a bigger gamut of, say, 6 colors. But in any case, whether we place a particular ink value on the page at a certain location or not is still a binary decision for each of those color inks that we want to use for printing. So what I'm going to show you here and now is in the course reader, which is completely online. All this is available, freely available online. So handout J in the course reader gives, and I'll show that in just a second, gives 3 different ways to perform this really severe quantization of an image down to 1 bit. Either it's on or it's off, or in other words, if it's printing, we're going to put ink on the page or not. If it's a monitor, we're going to put a white dot on a black background or not. Okay, so it's the same duals, whether we're printing or displaying on the screen or a other handheld device, for example. Okay, so let's look at handout J. So for handout J, I use a classical image used widely in image processing. This is a Lena image, and what I show on the bottom here is the original, and then on the top 3 pictures are different ways to convert this grayscale image into binary images. And again, the binary images are useful for printing and display. So for example, if I have a micromirror device for handheld, that mirror either reflects light or not, and each micromirror is tuned to a particular color. So it tells me whether or not I'm going to have color at a certain pixel on my screen. And then the pixels on your micromirror device are chosen to be smaller than you can see. And so what your eyes will do is aggregate enough of these micropixels to make one pixel you can see, which combines all the color, which are all binarized, around it in, say, a 3x3 grid, in which your eyes actually sees the average color in that pixel, which is now made of 3x3 or more of these subpixels or micropixels. All right, but anyway, in the bottom line, we need to get to a binary image to make all this work. And so here are 3 ways we can do it, 3 very common ways to do it. So first of all, this image that I show here of Lena on the bottom here is going to be a grayscale image. It's 8 bits, so it's unsigned, which means I have values from 0 to 255 inclusive, 8 bits or 256 levels, and 0 is the background intensity and 255 is the foreground. And what background and foreground means varies with printing or display. So in this case, I have at each pixel location in the Lena image on the bottom here, I have a value from 0 to 255 inclusive. What I like to do is convert that to a 0 or a 1. And again, 0 is typically our background intensity, and 1 would be the foreground intensity. So for the purposes of display, the background intensity would be 0, and the foreground will be white. So again, it's the opposite in printing. All right, so here's the first thing we can do is just threshold the image and say, well, if the image values are between 0 and 255 inclusive, then if I just threshold at the midpoint, the mid-gray value, we'll call it maybe 120, it's 127, I suppose, 0.5. So we could say, okay, if it's greater than or equal to 128, we'll make it 1, and if it's less than 128, we'll make it 0. And if we just apply this binary decision by using a single threshold value across the entire image, I get the simple threshold result on the left. Okay, so here's my simple threshold result. And if you'll notice that since I'm applying the same mid-gray threshold across the image, I lose a lot of details. So anything that is very close to white becomes white, anything really close to black becomes black, but also mid-gray values, especially those close to the threshold, which could really go either way since they're close to the threshold, are forced to go either black or white because this threshold is a hard threshold with only one value of 128. So what we get as a result is a pretty washed out scene. We lose a lot of detail in this scene. We lose a lot of the detail here, for example, in the feather and on the hat. We lose a lot of some details on the face. It's kind of washed out. And we do reserve, so certainly some edges that get preserved even after thresholding. But overall, this is not a high quality rendering of the actual image. You could argue, well, I like the effect and that's fine, but as far as showing this to millions of consumers, which of these 3 halftones they would like, you're not going to get many people picking the simple threshold. We've done human subjective tests on this, and they're just not going to pick the simple threshold, as well as other authors for many, many years. So the next step up is, or the next more complicated approach is clustered dot dither, and the idea here is twofold. One is to have thresholds that vary over space, so you can pick up more detail. It's not just fixed to one value. It might take one of, say, 16 values, and we'll talk more about that in coming slides. And that's called, in general, ordered dither. This particular type of periodic thresholding is called cluster dot, and the idea here is to have the black, so in this case, I could argue either way, but the ones that become, the pixels that get turned on in this binary image are going to cluster together. And the idea is that for printing, if we put a bunch of ink on the page, we're going to get some spreading of that ink once it hits the page. So the idea is to cluster those pixels that would get printed in ink on the page so that when the ink spreads, they just spread into neighboring pixels instead of creating a blob that isn't exactly the intensity that we wanted. So this is cluster dot dither has been used in printmaking for, I think, since 1852 or something, a long time. Certainly in the late 1800s, it's been around a long time for printing newspapers. Not a new technique by any means. But anyway, so what you see here is cluster dot dither, and it's certainly much better rendering of the details of the image versus the simple threshold. We can certainly pick up a lot more. We can pick up more detail again in the feathers on the cap. We can pick up more details in the eyes, subtleties in some of the skin tones. Again, this is all gray level. This is all 0 to 255. more details in the hats and also in the background. So it's a little bit more closer rendering of the original image. By no means as good as the original image, or even very close, but it's really a lot better than a simple threshold. The last option here on the right is called error diffusion. This was invented in 1976, and the authors are Floyd and Steinberg on this paper. They sort of, by trial and error, found a really nice method to control where this quantization error goes. So what happens if you go back to simple thresholding, if I just threshold with one value, then what I'm doing is I'm generating quantization noise or quantization error whose frequencies spread out over all the frequencies and kind of just wash out high frequencies as well as low frequencies. It turns out our human visual system is more sensitive to low frequencies than high. It's more or less a low-pass response to a first-order LTI approximation. So the authors of this paper for error diffusion said, well, let's at least see if we can control the quantization error that we introduce so that a quantization error is shaped into high frequencies where we're less sensitive as humans to that quantization error. So what you see in error diffusion here is, again, so you see more detail than simple thresholding. Again, the feather and the cap, more skin tones, more detail on the hat, and so forth. What you also don't have versus clustered dot dither. Clustered dot dither, if you look at this, has sort of a screening effect. It looks like I'm viewing the image through a screen, like a screen that we might have in a window to keep out insects. So this screening technique, which really, it really is a screening technique in original newspapers and magazines, is an artifact, and we may be used to it from seeing it enough in print media, but nonetheless it's still an artifact. So error diffusion gets rid of this periodic artifact, which really comes from resampling due to the periodic nature of the thresholds that we're using, and instead trades that off for a little bit more background noise. So you see a little bit more, if you look at the handout more carefully, you'll see a bunch of pattern. They're not periodic, but you'll see these patterns of white dots. So there still gets some patterning. There's some artificial patterns that are introduced. They're not periodic like over the whole image, but they're locally periodic to some feature in the image. So the trade-off here is a little better visual rendering of the original image, better than clustered dot dither, get rid of the screening, but instead we pick up other artifacts. We trade one set of artifacts for another. This error diffusion is computationally very simple. It's a thresholding operation like the other two methods, but then we feed back that quantization error and filter it so that we shape that quantization noise into high frequencies. Okay, so let's explain a little bit more about these different methods that you've just seen visually. Okay, so for, again, the first method was that just one fixed threshold over the whole image. Again, the image is 8 bits, 256 levels from 0 to 255 inclusive. So again, we take grade levels from 128 to 255. They become 1, which is white in the case of a display, and it might be the opposite typically for printing. But so grade levels 0 to 127 get mapped to 0. So it's a hard threshold against 128, and again, any greater than or equal to 128 becomes a value of 1. Now, in implementation, just as an aside, as far as actually implementing some of these things, we might internally represent black as -1 and white as 1. It just allows us to get rid of a DC component, and that's something that we use in error diffusion, but that's an implementation detail. That's an aside. Okay, for ordered dither, this is this screening effect that, again, commonly used back in the day for magazines and print media. This is periodically spatially varying thresholding. And what this is interesting, there are a couple ways you can look at this. Is one way is that by varying the threshold over space, what you've really done is you've essentially added spatially varying noise to this. One way to look at it. You can also look at it as a resampling operation because in our case, the thresholds are, and I'll show you examples of this, are periodic. It's as if we've resampled the image in these blocks of thresholds, and the block corresponds to the one period in space. So the example in the that I showed you from handout J uses a very, very small periodicity. It's only a 4x4 mask, so I have over a 4x4 region different thresholds, and then I simply move that 4x4 mask over the whole image and threshold every pixel to get the binarized image. And you'll see, again, as I mentioned already, that you get these periodic artifacts as if the screen had been overlaid on the image. And there's no noise shaping, so whatever noise happens. There's no filtering or feedback mechanism to shape that quantization noise into high frequencies. You just get what you get on this one. Now, there are some breakthroughs in ordered dither that came about in the early 1990s, and this is to use very large masks that are 256 by 256 or even bigger, that are big enough that your eyes are not very sensitive to the periodicity. And this is called blue noise masking, and that's a very popular technique to this day. Okay. But anyway, this is an example to use a small mask just to make those visual artifacts obvious and visible. Okay, so air diffusion is the third method from handout J. This is the one that I would argue looked better, but it got rid of the washing out of simple threshold, and it got rid of the periodic artifacts for the ordered dither or cluster dot approach. So air diffusion here is going to essentially pass the original pretty well. The original image gets passed pretty well. There's two visual changes. One is that the original is sharpened, and that sharpening depends on the type of feedback filter. For Floyd-Steinberg, this is a mild sharpening, but for other methods, this can be fairly significant sharpening. Plus, we have this high-frequency noise, which comes from the quantization noise being fed back and filtered so that this noise becomes high-pass. So this is, again, we're trading one artifact off for another. And again, the insight for why the noise shaping approach is useful and for image display and printing is that the human visual system is, as I said earlier, is less sensitive to high frequency noise. And this is also true for the auditory system. And the example that I showed on handout J is a very simple feedback. The filter in the feedback loop only has 4 coefficients. It is very simple to implement. Those coefficients are all power of 2 or sum of power of 2 values. Very simple to implement in any sort of system for high-speed display or printing. Now, it's actually an FIR filter, but because it's in a feedback loop, it behaves as if it were infinite impulse response. If you look at input to output characteristics where the input is the input image and the output is the binarized image. So if we look at that system, then it turns out this FIR filter, and I'll give you the block diagram in a couple slides, although the filter itself is finite impulse response, because it's in the feedback loop, it actually behaves as an infinite impulse response filter. Now, if we look at the image quality of those halftones, you can, again, these are the same, kind of review what I just said when we went over handout J, is that, so the simple thresholding idea is pretty low quality. The quantization error is spread equally over all frequencies. We don't care if it affects low or high frequencies. Both will be affected equally well, but our visual system is, again, more sensitive to low frequencies. The second option was ordered dither, medium quality, again, not much more complexity to implement than the simple thresholding, but this resampling from this periodic overlay of this matrix or block of threshold values causes aliasing. That aliasing looks like this gridding effect or screening effect. And the last one is error diffusion. This is higher quality, again, because this quantization error is controlled, and by choosing the error filter, you decide not only the amount of sharpening you're willing to use or experience, but also how the quantization noise is shaped. Now, one of the nice things about error diffusion is that we can actually compensate completely through LTI filtering. So completely is a little strong. We can compensate very well through either adaptive filtering while we're doing the halftoning or pre-filtering before we do the halftoning to actually compensate for the sharpening and error diffusion. So it's a very simple LTI filter we can use. It's no more complicated than the actual feedback filter here in the feedback loop, excuse me, to compensate for the sharpening. So we can control the sharpening in error diffusion, which is pretty nice. Now, the whole kind of where all this got, where the nice connection comes in is this the idea of error diffusion, which is, again, shaping the quantization noise through feedback. This is also known as noise shaping feedback coding, is a key principle in both analog to digital and digital analog converters. So a lot of the effort in audio data converters has been applied, my research group has applied it as well, to this case of error diffusion. So very nice analogies between the two. All right, so here are another couple of examples for halftoning. I don't show you the original, but it's the face of a baby. And again, it gives you some different methods out there and you can judge the quality, of course. And it's better to judge this by getting handout J, or getting the slides and making sure that you're viewing them at 100% so that there's no resampling happening while you're viewing the images. So have a controlled environment. When I showed you handout J, I made sure that I was at 100% for the PDF display to prevent any resampling artifacts from the PDF display or the Adobe software. Not Adobe's fault, it's just a factor of resampling to fit the screen size that you want, or window size. Okay, so here's some ideas. Again, different types of visual artifacts. We have the two here that are going to be based on these periodically varying thresholds, and we get screening effects, or just different kinds of screening effects. The one on the left, the cluster dot, again, is going to try to cluster the on dots, which means the off dots also may cluster, but we're trying to cluster the on dots. And this is the clustering here is for printing. Dispersed dots a little better for monitors, because for monitors you have much better control over the pixel rendering based on how much money you put into the monitor. Then there's so those first two methods are both types of periodically varying screening approaches. The one on the far right here, error diffusion, again, I have 75 there, but it's really should be 76, I think, for the Floyd and Steinberg paper. And so again, the idea is to basically again feedback the quantization error and filter it. This is a blue noise mask. I had mentioned this earlier. This is using very large periodic arrays, so 256 by 256 or 512 by 512. And again, the idea there is to have the periodicity spatially so large that your eyes are not very sensitive to it. And this goes back to how when we view images, we tend to focus on one part of it. And again, at the viewing distance of about 30 centimeters, it's about the size of our thumbnail. So that's where really our highest resolution, and our resolution in looking at a scene falls off exponentially away from the point of focus. So the idea is to create these blue noise masks about the size of what would impinge on your fovea when viewing a printed document or looking at a display. So it was a really nice breakthrough in the early 90s. So again, if you look at the image, you don't see, at least I don't see, the gridding effect that I would see in a cluster dot. So basically so the blue noise mask is this periodically varying thresholds, but I don't see the gridding effect that I see here with the smaller threshold array sizes. Green noise takes the idea of error diffusion one step further. So instead of just feeding back the quantization error to the input, it also feeds back the output image to the input to the quantizer, and it allows you to basically control the quantization noise. So for blue noise, this would be high frequency noise, and for green noise, this is basically from the color green, is basically mid-frequency noise. So it's a different kind of shaping than the blue noise effect of either error diffusion or blue noise mask, and it's also a very effective technique and not very complicated. It's a couple of extra multiply adds per pixel versus, say, error diffusion. The last one is an iterative method, which kind of gives us an idea of what's the best we can do. This imposes a human visual system model on the updates, and it basically just searches and toggles bits from 0 to 1, and 0 to 1 and 1 to 0. It also swaps bits, but it does this in a way to try to drive down an error function to 0. And an error function is the perceptual distance between the halftone and the original. And so they pass each image through a model of the human visual system, an LTI model, and then compare it basically as a mean squared error on the difference. And this is iterative, and it may take many minutes to get to get an image versus almost, a matter of, milliseconds to get an air diffused image. All right, so it's more complicated, but it gives you an idea of what's the best you can do. All right, so let's kind of look a little bit more at these methods. Again, we're trying to get insight here for visual insight on in general data conversion, which we'll do in part 2 for one-dimensional signals. So again, the idea here is to vary the threshold over space, and we'll do this later on in part 2 by adding noise to the input to the quantizer, which actually ends up changing the threshold value. And by doing that, we can actually remove or at least mask harmonics that occur through quantization. All right, so here's a periodic array of thresholds. This is, again, you can do this for clustered dot screens or dispersed dot screens. And this really is a spatial resampling effect that leads to this gridding effect. Okay, so here's an example of a clustered dot screen and a dispersed dot. So let me do dispersed dots a little easier to see. So for dispersed dot, I have this 4x4 mask, and I'm going to take this 4x4 mask and I'm going to repeat it. So I'll take the 4x4 mask and then move it to the right by 4 pixels and apply it, and to the right by 4 pixels and apply it until I've covered the whole image. And the way I choose the thresholds is I order them, and here I've ordered them 1 through 16. And what that really means is that each of these is really a lookup. So this is just, I'm ordering them from 1 to 16, but what does 1 mean? Well, 1 means, it means this threshold. So if I have 8-bit image, which is 256 values, then my threshold will be for the number 1 entry corresponds to the threshold. This is the number 1 entry. Is 1 over 32 times 256, so 8. Okay, so 1 maps to 8. And then index 2. Here's index 2. So this maps to 24, and so forth. So we get all the thresholds here. They're uniformly spaced, thresholding, but the way they're chosen, if I were to look at a gray value that, say, is at 128, mid-gray, in my grayscale image of 256 levels, then what will turn on is all the pixels that are shaded. So these all will turn on in a checkerboard pattern. And if you look at the average value across, so what is it? Well, half the time it's 0, half the time it's 1. It's going to look like, on average, half the average between white and black. So it's going to look like mid-gray. And so that's the idea, is that the way the thresholds are chosen to get the binarized image will look to the eye like the average value in that local region. And so even though it's binarized, it will look like a grayscale value when we view it. And in this case, that grayscale value, with half the pixels turned on, half the pixels turned off, or half the pixels black, half the pixels white, the average value would be the midpoint, which would be 128 in terms of levels 0 to 55. In our system, if our values were 0 and 1, then the average value would be 1/2, which is, again, is the mid-gray, if 0 is black and white and 1 is white. Okay. So again, the idea here is to take these masks and apply them periodically across the image. So the threshold at any point, excuse me, in the image that we're going to apply it to is going to vary with space. Now, grayscale area diffusion is much more related to what we're going to talk about in part 2, because in grayscale area diffusion, again, we're going to control what happens to the quantization error explicitly. So we're going to shape the quantization error or quantization noise into high frequencies where the human visual system is less sensitive. This is a type of what's called sigma delta modulation, and you'll see from the loop that we have a sigma and a delta. So a sigma is the summation, and the delta, okay. So here's the difference, and this would be the sum, if you wish. Here, I know it's also a difference. In continuous time, there would be an integrator in the loop and a quantization error calculation in the feedback. So the integrator was the sigma, and the quantization error calculation is the delta. Okay, so the two parameters we really have, actually about the only freedom we have in this block diagram is the choice of the error filter. And this error filter in isolation is low pass, but then we put it in a feedback loop and it takes on a different signal transfer function. And that signal transfer function is more or less all pass with a little bit of sharpening at higher frequencies. Excuse me. So here's the let me go through it's a very, very simple block diagram, but nonetheless fairly hard to analyze because of the quantization. So I had the original image here, which is X. This is the grayscale image. And let's not worry about the feedback for just this first pixel. So the first pixel comes through, and we quantize to either white or black. Okay, so in implementation, what we tend to do is, again, use 1 for, I suppose, white and -1 for black, or it could be the other way around, +1 and -1. Depends on whether it's printing or display. So this binary image tends to be either +1 or -1 in an implementation. And we feed back the error, then is simply the difference between the output of the quantizer and the input, just like we did in Lecture 8. This quantization error is fed back and filtered by our error filter. Again, the error filter in isolation is low pass, but again, the configuration is a little more complicated. I'll give you that in just a second. So we do the filtering here, and we subtract out what comes from the output of the error filter from the next pixel. So we basically feed the quantization error forward to the unquantized or unhalftoned, the grayscale pixel values that haven't been halftoned yet. And this allows us to, again, shape this quantization error into high frequencies. So visually, what does this look like? Well, here's, again, the same face of the baby on the right, and as an image, and if we take the Fourier transform magnitude and we square it to get a spectrum, and then we move DC to the middle, then what we see is, it's hard to really see that. I'll do it with the mouse. What we see is that in the middle, we end up, so that's DC. So the image in this case is, most of its energy is actually around DC. So what will happen is in the halftone, most of the energy around low frequencies of that original input image comes through, and then we get this bed of noise at high frequency, which you see out here. So we have this little bit of kind of low amplitude noise in the background, and then we have this high amplitude noise at high frequencies. Again, 0 frequencies in the middle for this plot. That frequency would be pi minus pi in the horizontal direction and pi and minus pi in the vertical direction. So again, 0 frequencies in the middle, and so most of the image around that's at low frequencies comes through. The image content at really high frequencies would be probably buried in the noise, given the amount of noise how much noise shaping that we're doing. Okay, so so how simple is the error filter? And all of this is pretty simple. It's a 4-tap FIR filter. It's in 2 dimensions, but the coefficients here are all sum of power of 2s or power of 2s. So I have 1/16, which is a power of 2. I have 7/16, which is what the sum of, 4/16, 2/16, and 1/16. So it's all sum of power of 2s. So this becomes a very fast implementation where we can replace multiplies with shifts if we're careful about it. All right, now for the signal transfer function, there's some, on the course website under the midterm 2 review, there are some problems for working out the signal transfer function, the noise transfer function, but I'll just go ahead and give you the answer here. And the way that we go about to get a transfer function, we can't just do that directly because we have a nonlinearity in the system. But it turns out this quantizer can be linearized, approximated as a linear function by the following idea. So if I have a quantizer, and in this case it's going to give me one of 2 levels, And again, in practice, it's actually +1 and -1, and we tend to implement these things. So I have x coming in, and here's my quantized output. I can approximate this over a region as a line. So I can approximate the quantization. It's a very crude approximation, but it works well at low frequencies, is simply as a gain. So I can replace the quantizer or I should say model is probably the better word, not replace. Model the quantizer, approximate the quantizer as a gain. So we can replace it with a gain of a constant k. And k depends on the error filter, oddly enough. So k for Floyd-Steinberg is 2, and for other error diffusion methods, I've seen k be 4 or 5. So it's not a million, but it's some value above 1. And then what happens is the noise transfer function, which is the easier one to derive, it's 1 minus the frequency response of the error filter. So again, if the error filter, so if H is, say H is ideal, low pass, then the noise transfer function, and this is 1, the noise transfer function would look like this. It would be a high-pass filter. So that's the easier part. Let me make this a little smaller. Okay, the signal transfer function is a little more complicated. Again, the noise transfer function is obtained here by replacing the noise with, sorry, the quantizer with additive noise. So for the noise transfer function idea, we're going to replace the quantizer. Again, remember, the quantizer can be viewed as adding some uniformly distributed random variable to the input. It's a random error, right, in the output. So you can replace the quantizer with a noise source and set the input to 1. And that means that the transfer function from the noise source, which is now where the quantizer is, and the output, which is the binarized image, this B of M here, this is a noise transfer function. So the quantization noise is shaped and made high frequency noise when it finally arrives at the output, which is our output here is the binarized image. For the signal transfer function, this is where we model the quantizer as a gain. And the signal transfer function is a little bit more complicated. This is the transfer function from the input signal, which is x of m, to the output, which is the binarized signal. That's our signal transfer function. And again, to get there, we have to model the quantizer as a gain. So we have two different models for the quantizer. The effect on the signal, the input image to the output image, is a gain. The effect of what happens to quantization noise, we replace the quantizer with an additive noise source. Excuse me. All right. So again, so let's kind of draw that out. If we look at the signal transfer function using the same ideal frequency response, then our signal transfer function for k is 2 looks like this. Okay. So that's our signal transfer function. It passes all frequencies, and you'll note that the higher frequencies are amplified. So low frequencies, all pass response, no change in amplitude. Higher frequencies are amplified. This is the sharpening effect, that the high frequencies get amplified, which results in a sharpened image. All right, so the last thing I want to do to wrap up, because again, part 2 will do the rest of this, I want to go to one slide toward the end of part 2 to show you the effect of noise shaping with a 1D signal, and it's pretty cool. Okay. So again, this particular example is due to Dr. Thomas Kite, who was my first PhD student. Okay, so this is a very simple example of noise shaping, and we're going to go back to 1D now. And the idea is that we have a 2-bit digital analog converter, and we have a 4-bit input signal. So again, we want to reduce the word length. So this is a halftone example, but instead of quantizing to 1 bit on the output, we're going to quantize to 2 bits on the output. And all the numbers here are going to be unsigned. Unsigned bit patterns, integers, whatever, word. So our input signal will be 4-bit words unsigned, and the output is 2-bit unsigned. What we'd like to do is not just have the quantization error go over all frequencies, which would be the result if we just kept the 2 most significant bits and threw out the 2 least significant bits. Instead, we want to feed back the bits that get dropped for future use in future decisions. So what we're going to do, so we take the high 2 bits, so this is the 2 most significant bits, go there, and the 2 least significant bits go here. And we're going to feed back the least significant bits that were thrown out when we went from 4 bits to 2, and we're going to feed that back to be used in future calculations. So we feed back these 2 least significant bits, and there's going to be 1 sample delay, so we're going to really feed that back for the next, when the next sample arrives, we'll add them together. So the next sample arrives, and we add the 2 bits that have been thrown out on the previous quantization operation, and we're going to add that to the current 4 bits, and then threshold, or then, actually in our case, keep the upper 2 bits and throw out the lower 2. And for the purpose of an example, I'm going to assume that the input is a constant, and this is same as 9. All right, so this equals 9. All right, so I have 1 bit in the least significant place, and I have a 1 bit most significant bit unsigned, so it means that I have 8 plus 1 is 9. So let's look at what happens when we go through this noise shaping example. So the first time tick, the upper input, which is the 4 full bits, is 9. The initial lower 2 bits we'll just set to 0. It's a good choice, why not? The sum gives us 9. We output 1 0 to the DAC, the upper 2 bits in the sum, and then we feed back the lower 2 bits that got thrown away. All right. So the 0, so the lower 2 bits go back here to be fed back, and the upper 2 bits go on to the DAC for output. Next time comes around, we get a new input sample. That new input sample is still 9, or 1001 in this unsigned binary format. I add the upper and lower inputs together, and I get 1010, so now I have 10. So the upper 2 bits, again, goes to the output, and the lower 2 bits are fed back. Next sample, next time step arrives, new input, we read the new input value. Well, the new input value is the same as the old input value. We add those together, we now get 11. So we take the upper 2 bits, that goes to the DAC, lower 2 bits is fed back for the next quantization operation. So next time arrives, input hasn't changed, it's still 9. We add 1, 1 to that. We now get 12. The upper 2 bits goes to the DAC, and the lower 2 bits gets fed back. But we'll notice the lower 2 bits is the same as when we started. So this thing repeats if the input doesn't change. And if you look at what happens, that over time, if you look at the outputs, we get 8. So again, remember, these are the most significant bits. So we get 8, 8, 8, and 12. Right. So I get 8, 8, 8, and 12. Average value is 9. So even though we've reduced the number of bits from 4 bits to 2 bits by using the feedback and filtering, turns out this delay here actually acts like in feedback as a filter, we retain the average value correctly, even though we've gone from 4 bits to 2. And it turns out, which is great, so we now have 4, even though we have a 2-bit DAC, we actually have 4 bits of resolution at DC. Now, more generally, if we go from 4 bits to 2 bits, we know from the quantization noise formula that the SNR for amplitude quantization is 6 dB per bit. So if we reduce 2 bits, we should lose 12 dB of SNR. Okay, so and if we don't do any noise shape feedback coding, then that loss goes over all frequencies equally. But with this noise shape feedback coding, then what we get is we don't lose anything at DC. DC is just as good as it was. And at low frequencies, we actually do better than 2 bits. At some point, because of the noise shaping, we hit a trade-off point where frequencies above that trade-off point are worse off than uniform quantization, than just quantizing and not feeding back the error. But the lower frequencies benefit quite a bit, and they have more bits of effective resolution than 2. So it's a trade-off. And again, for our cases, for audio and image processing, our human systems are more sensitive to low frequencies than high, so this trade-off is worth it. We'd rather have more accuracy in low frequencies and less accuracy in high frequencies. Okay, so that concludes Lecture 10, Part 1, and I invite you to look at Lecture 10, Part 2, which will cover the rest of the slides here in the slide deck. And as usual, everything here is online on the course website, and that's pointed to you back wherever the video is available on the internet. Thank you very much for attending.